So the class today, we will speak about Apache Pig. Actually, let me just quickly see. Okay, maybe someone could test my audio, see if I can hear you. So say hello.
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 Gracias. Okay, so we're good. We'll talk about Apache Pig today. So the objective is to somehow simplify the way we program Hadoop jobs. So if we think about Hadoop versus SQL, in Hadoop, you have to write quite a lot of Java code, and there's quite a lot of boilerplate code, and you need to configure what are the mappers, what are the reducers you will use, whether or not you'll use a combiner, and put all of these things together. So it's maybe not the most intuitive, although it is the kind of standard way it would be done in production for coding Hadoop jobs. It can be, there's quite a lot of syntax and boilerplate code to add. So if we were to think about writing something in SQL, this is essentially an SQL query that's equivalent to what you're looking at in Lab 3 at the moment. So you would just specify what you want, it being a declarative language, and thereafter the system would process the query and generate in this case, the actors and the pairs of actors and actresses that have appeared together in the most number of movies. And we can order that descending then to see the top pairs of actors and actresses. So it would be quite a lot simpler to write an SQL query, right? So why don't we just use SQL? Why am I torturing you by asking you to code Hadoop jobs? Would it work okay if we were to load the data into Postgres and run the SQL query? So why not use SQL? The first answer is that relational databases are typically not built for very large workloads over lots of data. So I've tried this. I've tried loading the data that we have in Lab 3 into Postgres and running this query. And it does run, but it takes several hours. And if the data were larger, the data essentially that you're working with in Lab 3, they're not super duper large. This is just to make the lab a little bit easier to do. You know, if you were to make the data larger, even larger, it would just take longer to process and create longer queues. So at some stage, the relational database will just stop working because of essentially you have these indexes on disk in your relational database, which are B+ trees. And the typical way that relational databases will work is using, depending on the type of join, but it can generate a lot of random accesses to disk that will just be slow because the disk arm has to move around to find the different data. So in general, they don't plan for large workloads. There are certain types of databases that are more optimized for analytical workloads, which is sort of processing all the data to get a result. But in general, these transactional databases, things like Postgres, for example, they would work much better if you were to specify, for example, a movie or a particular actor here, in which case it could find just that data, and then it could do the joins to find the other people who acted together with that actor, and so forth. But here we're actually processing, the entire data set pretty much, right? So they're not built for that. So this is an answer for why we don't use relational database engines, but not an answer for why we don't use SQL, the language. Why don't we just have a language like this and maybe try to compile it into Hadoop, right? Into Hadoop jobs. So actually we could do that. That seems feasible. So we write this, and then instead of evaluating in a relational database engine, we translate it to Hadoop jobs and evaluate it on the Hadoop cluster. So that is the fundamental idea behind two languages in particular that have been proposed. One of those is Apache Pig. So we'll talk about that first, and I'll give a brief mention to Apache Hive at the end, which has a very similar idea. So Apache Pig, the idea is to somehow use something that's more familiar to SQL. It's not exactly SQL, but so we're going to create MapReduce programs to run on Hadoop, but we're going to use a high-level scripting language that's called Pig Latin. And the idea will be that the scripts we write in this language will be translated to MapReduce jobs in Java and run on Hadoop. So if we need to, we can also, if we need some special Java code or Python or Ruby or whatever, we can implement user-defined functions that do specific functions in case there's something we need that's not in the scripting language. So the overall language or framework of Apache Pig is based on a concept called Pig relations. Relations as in relational databases in a table. So it's based on tables. So why is it called Pig Latin? Atwe language istai. I'm not sure if you've seen something like this before. Do you know what language this is?
It looks like, I don't know.
So it's called Pig Latin. So it's a game that children play to try to talk to each other without their parents realizing what they're talking about. The idea is essentially you just take the start of the word, you stick it on the end. So this is what. So you take the start of the word, you stick it on the end, and then you add an A at the end. It's supposed to sound kind of playfully as if people were speaking Latin, but that doesn't really work as far as I'm concerned. So anyways, this is Pig Latin. It's a sort of a fictitious or language used in games in English. I don't know if there's something similar in Spanish, but so that's the origin of Pig Latin. So okay, so you can study that maybe a little bit later if it's in that. Okay, there's another example. Chicken soup becomes ikenche upse. Ikenche upse. So you just take the start, put it on the end, and then append an A. AY. Okay, very important. So we'll move to Apache Pig. We'll see a first example. So what we're going to do is we have a large, let's assume you're working for a supermarket chain. We have a large file which contains transactions with a column for the customer, some customer ID, or it could be a receipt ID, for example. We have a list of the item names. We have a list of the date and time of the transaction and the price of that item. Okay, so this is obviously not normalized, this table, but we have this very large transactional file here called transact.txt. Let's say it's in tab separated values TSV. So what we'd like to know is somehow find the number of items sold per hour of the day. Okay, so we'd like to know how many items are we selling in each hour of the day. So let's have a look at how we would implement that in Pig. So the first thing that you will not always need in Pig, but we can define, in this case, I assume it's in Java, but we can define a list of functions that we can use in our Pig script. These can be user-defined functions written in Java or Python or Ruby or whatever, but in this case, we'll assume Java. How it's implemented, you implement a class that extends a certain class defined by the Pig library that you'll need to import. And within that, you have this exec function, which receives a tuple, which is a row of the table. And in this case, it will return a string. Okay. So based on this input, you do whatever processing you want, and you return the value of this type. So in this case, what we're doing is we're extracting an hour. So we're going to essentially get the first element of the tuple, and then we're going to extract the number. So this is an example. In general, in many tasks, you won't need a user-defined function, but you can use them if you want. So afterwards, what we're going to do after registering these sort of library of functions that we might use for example, transforming or extracting data from tuples, we can load the entire Pig relation, the whole table, into Pig. So what do I mean by load? I don't mean load into memory. It just means essentially that Pig will open the file. It's not going to load everything into memory. It's not even going to read the file. It's not going to do anything for the moment. But what we can do is define a schema. So we can say that this table is separated with tabs, and we have 4 columns, and we're going to call the 4 columns customer, item, time, and price. It's not necessary that the file contains a first row with the header or anything like that. It can start directly with the data. So we call this raw, we'll call the raw data, the relation raw. So this will this will open what we would call a streaming relation. So that relation isn't loaded into memory or anything, but we're going to be able to read this relation tuple by tuple, row by row. So this is essentially the view, but we have to imagine again that it's not loaded into memory, but we can start to iterate row by row over this relation. And this is the sort of view that we'll have on the relation. So we have a table, right? Customer, item, time, and price corresponding to what we've defined here. And these are the 4 elements of the tab separated, 4 columns of the tab separated values file. So this is our Pig relation. So let's say we're only interested, I didn't mention this in the question, but we're only interested in items that are above a certain price. So we can define a user-defined function. In this case, we define a user-defined function just because in our data, we have these $signs and dots and so forth. So we can't, otherwise we could use a condition in Pig to filter. But in this case, for the example, we'll just say that we're going to use a user-defined function to select those values that have the price of at least 1,000, which means that we're going to get rid of the first item here. By the way, I have no idea if these prices reflect reality or not. But anyway, so we're going to remove this first item here because it doesn't match the condition. And okay, so now we have a new relation, streaming virtual relation, let's say. So next we will take the hours out of the time. So we're not interested in the exact time, just the 08 part, what hour of the day it is. So we'll use a custom user-defined function for that. So we run that and we convert now into a new relation called hourly here, where we've transformed the hour. Next, we're going to remove any duplicate items. So what this means is if we have one customer who buys the same item several times, we just want to count it once. Okay. So in this case, we do distinct, which means that essentially we're going to get rid of entire tuples that are duplicated. So in this case, we see that the first tuple and the second tuple are duplicated. So we'll just remove that tuple. And then we want to start doing our count, right? So we're interested in counting the items per hour, right? So what we want to know, for example, is how many times Nescafe was bought at 8 o'clock, between 8 o'clock and 9 o'clock in the morning. So for that, we're going to group by both item and hour, okay? So we group by item and hour, and it gives us a table that looks a little bit difficult to draw, but here's in 2 dimensions, but here's an effort. So here we have the group key, which is item hour, and then we have all the tuples that have item equals Nescafe and hour equals 8. So essentially we get grouped here all of the tuples associated with this group key, okay? And then we have the next group key, which is 400 grams of carrots bought at 8 in the morning, and so on for all the keys. So essentially we're grouping all of the tuples according to their item and hour in which they were purchased. Then for each, we're not really interested in all this data. We just want to count how many tuples there are in here. So we use this, this function here, which will generate for each tuple in the H or item, our item, we are going to generate the key, which is, okay, flat and 0, which I'll talk about in a little bit more detail, and count. So we're going to count how many elements there are in here, intuitively speaking. So a row here, it's important to mention, is the entire thing. So like this block here, it might not be super clear, but actually what we have is a key that's, okay, this pair here, a tuple, and we have a value that's a set of tuples. And I'll have to talk about that a little bit more in the class. But essentially one row here of this table is this whole block here associated with each key. So for each row, we're going to generate the key, and we're going to append the count, how many things there are here. So what we'll get as a result, counting this here and counting each group likewise, will be a relation like this, where we have a tuple of two things and then a count. Okay. And finally, what we would need to do is to sort the items and the hours by the count, because we want to see what are the most bought items in a particular hour. Okay. So we do that descending, and we'll get, okay, here. It depends, of course, if there are more data, then there might be some other value here, but just within what we can see, then we'll have Nescafe first because it is 3, and Zanahori second because it has 1. Then we can save that to a disk by using store. So that will save or output as a TSV tab separated file to HDFS. So the idea in general, it's not actually necessary, but the idea would be that we'll be reading this file from HDFS and writing our file, our output file, to HDFS. Okay. So there's some details I know that are not, going to be super intuitive right now, that I'll have to explain in more detail, which will be kind of part of the class. But this is to give a flavor of the language, where what we're doing really is defining transformations of relations on each line. So in every line, we define a new relation that somehow transforms some of the one or more of the relations that precedes it. So this is a sort of a flavor of Pig. It's not super SQL-y, but it's a bit more high level. It's kind of a mix between a sort of declarative and imperative language in a way. So you're kind of still defining the steps, but there's a lot of details on how it will be evaluated that the Pig framework will decide when it compiles this script into Java Hadoop MapReduce tasks. So this is just a general flavor, and there's some details we'll get into. Any questions for the moment? Okay, so some of the main questions I spoke about here, there's tuples, and I spoke about how we can have values in cells that are sets, what this thing exactly here is and so forth. So we'll get to those details as well as talking about what the functions do. So the first thing we'll talk about is the schema. So it's relatively intuitive in the sense that we have Pig relations, which are just tables. The tuples can be incomplete, so we can have nulls. And the relations are by default unordered. So they'll usually be read though in the same order as they are in the input file, but there's no defined order, let's say. We can order them if we want, like in SQL. So the Pig schema itself is just associates a set of, or a tuple, I should say, of attributes, or a list of columns for the table. So this is essentially what we define. We don't in SQL, we can define keys and foreign keys and so forth. We don't have those sorts of notions in Pig. We don't generally need them. We do, however, have a domain. So we'll come back to that later. It's not, we can define what types the columns are, like, are they numbers, are they strings, what are they? We'll come back to that later. So if we want to reference a particular column, we can do that in two different ways. We can reference using the name. So we can say, okay, we want to filter by price on this column called price, okay, using that from the schema, or by position. So we can say $3, okay, which would be the fourth column. So in general, this is much preferred because it's much more readable if you're reading a Pig script. Much easier as well, I would say, to code, to actually use the names of columns. If you use this, then the $sign starts with 0. So 0 will be the first column here. In general, why would we ever use position? In some cases, we might do certain types of transformations where it's not actually clear what the name of the column will be after we're done messing with it. So we might do several processes and then create a group by key and then flatten that. And so in some cases, it might not be clear what is the name, in which case we can use just $0, for example, or $1. Okay. But in general, sorry, if you know the name, use the name. So you can use price. Okay, so I spoke about a domain. A domain in SQL would be varchar, int, and so forth, defining the types. So we can do something similar in Pig. The names are slightly different. So a string is called a char array rather than varchar or char array. We have date times, and we have time defined as a date time and price as an int. Actually, in our example, we had it as a string, but in this case, we'll assume it's an int. So what are the types we can have? Int, long, float, double, big integer, big decimal, boolean, char array, byte array, and date type. So these are the standard types. What happens if you omit types? So actually in the example I showed you earlier, we didn't specify the types. So what happens is if you don't specify the types, we use fields that default to byte array. So they're just considered to be an array of bytes of any representing any sort of data. And if we need, we can do implicit conversions, which is called various things, but duck typing is a common name for this. So there's this phrase in English, if it looks like a duck and it quacks like a duck, then it's probably a duck. So if it looks like a float and it quacks like a float, probably it's a float. So what does it mean? It means essentially, for example, if we load our hour here and we haven't specified what type it is, if we try to apply some sort of integer arithmetic to it, and if it looks syntactically okay, then we'll consider the hour here to be an integer. If we apply some float arithmetic to it, then we're going to assume it's a float. So if you're unclear about how the type will be interpreted and you want to avoid any misinterpretations, for example, the concatenate symbol can also be used for strings. If you're unsure, in general, I think it's a good practice to define the types of your columns. Okay. Any questions?
Profe,
Sí.
¿es posible hacer un join con un origen de datos relacional en este momento en el script?
So
Una
Pig.
mezcla.
So what you're talking about is you have your data in a relational database and you want to use that as an input. You want to use a relational database as input for Pig?
No, si es que el mismo
No.
Pig podría en este momento, dentro de un script, hacer un join a una base de datos relacional.
So you can do joins, but to do a join with a relational database, the easiest would be to output your data into TSV, so to export your tables to TSV. But that said, Pig has a lot of extensions, and it can read from a lot of NoSQL databases, for example. I wouldn't be surprised if there were some, there is probably some extension that would allow you to read directly from a relational database, but it would be something a little bit more specialized. So in any case, what you could do is just dump your whatever tables you want to join with. You could dump it to a TSV file, store it on HDFS, and then process that. If you can read, whether or not you can read directly from a relational database, I would be surprised if there weren't an extension, but I don't think it's part of the standard Pig framework, let's say.
Okay, gracias.
More questions or? Okay, so I spoke at the start about how there might have been some details that were unclear in the example and the way I drew the table, so we can see a bit more of the syntax of different complex types, so in particular tuples and bags. So the first one will be tuple, where we can define a table where cells contain or columns contain tuples of data. So in this case, what we have are just some raw data, and this is the sort of syntax that Pig uses to represent data. So if we look at what kind of data we have here, what we have essentially is a table with the 2 columns, where each column contains a tuple of 3 elements. So if we were to define a schema to sort of accommodate these data, what we would have here is our 2 tuples, T1 and T2. And within that tuple, there are 3 ints. So we call these T1, T1A, T1B, T1C are the names that we assign in the schema. We could change these, right? So what's important here is the domain of type of tuple. So we have a tuple here with 3 elements, and we have a tuple here with 3 elements. Okay. So this is sort of like how it would be depicted. So we have T1, and then it sort of has these subcolumns, which are the elements of the tuple. Okay. T1A, T1B, T1C. So we see that these data here correspond to the 3 rows we have here. These 2 columns here correspond to T1 and T2, and within each we have 3 values, T1A, T1B, T1C. So we can, this whole thing here, this tuple of 3 values itself becomes a value that we can use. Okay, so we can have tuples as values. So if we dump this is how Pig, you could call these methods in Pig. This is how the Pig would print the data that we've loaded. This is in general used to apply projections or transformations for each line by line. So we take a tuple, and for each row, we transform that row. The most typical operation to transform is to project, right? So we're just going to say here from A, what we want to generate is we want to project T1, T1A, okay, which is this thing here, and then T2, 0, which is the first element of the tuple of T2. So what would we get as an output? Or X will essentially project these 2 columns and produce this relation here. So in this case, it might not be super clear what this would be called, but these columns would be called T1.T1A and T2.T2A. But in this case, this sort of case, we might actually just prefer to use a numeric reference for them. Or we can also rename columns. We can do T1, T1A as A, and T2.T2A as B, for example, to make it clearer. So we dump this, and we see that we just have a typical relation with 2 columns. Okay, so here we have a standard kind of flat representation of data. So if we load this in, we get a standard kind of typical, we're loading them in as ints in this case, a standard relation. If we group by C1, the first column here, we'll get how many rows in B, in the output relation. So if we group A by C1, we will get the number of unique values we have in what we're grouping by. So we would get 3 rows. Right? So here's what the 3 rows look like. And what we see is that we have this slightly weird thing here where we have a sort of nested table. Okay. So what this is trying to depict, this is just my depiction, right? But what this is trying to depict is that actually every key that we're grouping by takes as a value something called a bag. Okay, so a bag is also called a multi-set. So what's the difference between a bag and a set? So we use the same notation here. We use braces to represent both sets and bags. A set cannot, they're both the same in the sense that they don't have order. The order does not matter. If we were to swap these two elements here, it would be the same bag. The difference is that sets don't permit duplicates and bags do. Bags allow you to count how many times an element appears in them. So we have bags. So what we have here is essentially we have the group by kind of key, and then the value will be a bag of tuples, and those tuples will be all of the rows essentially of the base relation that have that value in the corresponding column. Okay. So here we need bags to represent this sort of aggregation. The exact same thing happens in SQL. The only difference is that you immediately in SQL, you have to apply an aggregation. So you can do group by and you'll generate some intermediate thing like this, but then immediately you have to count, or you have to apply a max, or you have to apply a sum, which essentially will convert your bag back down into a simple value or a simple tuple. So what I want to say with that is you have the same thing happen in SQL, but you have no choice but to immediately transform or flatten that back down to a simple value or a simple tuple. In Pig, you can generate this relation and it's stored as any other relation, just that you have this sort of bag data type here. Okay, so here we have a bag of tuples. Okay, any questions or doubts about that? Okay, so the point being in SQL, you do generate something the same as this when you do a group by, but you never work with that sort of structure because you always immediately flatten it with an aggregation like count or max or min or sum that can take a tuple of values or a tuple of, a bag of values or a bag of tuples and reduce them down to a single count for each group or a single max for each group and so forth. In Pig, we can store and work with these sorts of groups of data. So the last complex type that I wanted to mention is map, but there's really not much to say about that because although the documentation provides some examples, it really doesn't say anything more about it. So it seems to have been some testing feature. In general, I don't see a whole lot of merit to using a map type either, because you can always, for example, join on something later. You know, you don't need maps in SQL, and in a similar light, you don't really need maps in Pig. You can just do a join on the key with something else if you want to. So there is some discussion in the documentation about maps, but in general, we won't use them, and they're not really discussed. So in terms of the three complex types, tuples and bags are the most important. So again, a tuple is essentially something like a row in a table or a list of fields, right? Where order matters, where the first element is distinguished from the second element and so forth. We have a bag, which is a set of tuples that allows duplicates. So we can have multiple times the same tuple. And then we have a map, which we're largely going to ignore, but it's a set of key value pairs. We're not going to use it. So the next thing would be, okay, let's say we have bags and we have tuples and we just want to get back to a simple relation, right? How do we do that? So there is a concept in Pig called flatten. So how flatten works is, okay, let's say we have just this base data here where we have two tuples. So what if we wanted to get back to a simple relation, right? So if we want to get back to a simple, this is how it looks in Pig. If we wanted to get back to a simple relation, what we can do is just use this flatten method. So what this will do effectively is unnest the tuple. And we'll generate an X such that essentially kind of maybe perhaps intuitively, this is what we'll generate. We'll generate a sort of a flat relation that has no tuples. It just has 6 direct columns of integers. So this is the idea of flatten, is somehow to always get back to a simpler relation. Okay, so we can dump that and we see now that we've dropped the nesting that we had before. So what about in the case of A here? So in this case, if we call, just for example, what happens if we call flatten just on one side? Okay, so we can do that, and then what we would end up with is a table that looks a bit more like this, where we still have this tuple, which is we still have 4 columns. The first column is a tuple, and then the latter 3 columns are integers. Okay, so we see that this is sort of like what, you know, syntactically what our data look like now. So we have a tuple of 3 elements, and then followed by 3 other integer elements. How long have I been speaking? Sorry. Let me check the time. Oh, okay. So let me speak for 2 more minutes and then we'll take a 10-minute break from 3:05 to 3:15. I lost track of the time slightly, sorry. So we can also flatten bags. So there is a slight difference between how we flatten bags and how we flatten tuples. So let's say we have our data here, which is a flat file, and then we do our group by as we saw before. So we group by the first column, and that creates this sort of structure here where we have keys that are integers and we have values that are bags of tuples. So, okay, let's say now we want to somehow flatten this structure back into a simple table. So we apply generate flatten A, and what we will get back essentially is the original table, right? So we'll just somehow take every tuple from the bag and just create a new row for that tuple in the table. So in this case here, we essentially return back to what we had before. So with group by, we can go from tuples to bags of tuples that are in groups, and then with flatten, we can go back from bags of tuples back to tuples. Okay. We dump and we see that we've got back the original data. It might not be in the same order. Actually, in this case, yeah, we have some change in the order, but we get back the same rows in some order. Okay, so in this case here, what we're doing is, what we saw was we went back to the original table, but you might think, what if we want to keep this other column here, right? So what we can do in that case would be, we can generate the group. This is a special name that's generated for the key of the group. And then we can just project as well, flatten A. So in this case, what we'll get back will be a relation with 4 columns, including a column for the group and 3 columns for the elements of the tuple. So we'll get back 4 rows in this case. So it's sort of like a roundabout way of copying the C1 column into another column called group, right? Which is, so I should mention that these examples are just to demonstrate as minimalistically as possible how flatten works. This is not, something you would probably use in a real script, but I just want to show what the flatten does conceptually. And then we dump and we see that we have our relation looks like this. Okay, any questions or doubts? Okay, so we'll take a break until 3:15. I'll put pause active as well in the chat. Okay. Any questions or doubts? Okay, so we'll talk about the operators briefly. In general, they're kind of intuitive, I guess. So for comparison, we can have equality, inequality, or not equals, or inequalities such as greater than, less than, greater than or equals, less than or equals, and we can do matches on strings based on regular expressions. We can also do some arithmetic, so some basic arithmetic at least. And we can have reference operators. These are sorts of, so if we have a tuple, we can use the dot to refer to a particular value within that tuple. Or if we have a map, which we're not considering in general, we can use a hash to refer to a particular value within that. So in terms of conditions, we can also combine them using typical Boolean combinations like and or not. We can also do casting, which can be useful, for example, if you load your data originally as a string and you want to convert it to an integer to be able to apply arithmetic, for example, you can apply some casting. So we also have some conditionals. So we can generate certain values based on a conditional statement. So in this case, we have a ternary operator, which has condition followed by a question mark. And then we give the value if true or the value if false. Essentially, that's what we have here. So what are we doing here? What we're doing is we're generating for an hour, which might be, for example, 23. What we're going to do is generate, if it's greater than 12, then we're going to add the value PM, or otherwise we're going to add the value AM. Okay. So we can also express cases. For example, we can check a case, and when it's something, then we return one value, or if it's something else, then we return another value. So we have ways of expressing conditionals, of returning a particular value based on whether a condition holds or not. We've seen grouping in the examples already. So we have 2 options for grouping. One is to group in a single relation, which is group premium by item hour, for example, we've seen in the example. So we can also co-group. We can group multiple relations, which would be essentially allow us to, it would be similar to doing a union of the relations and then grouping them. So we can group multiple relations, generating one relation with the groups from both relations together. So in this case, we can apply co-group over one relation which is premium and another relation which is cheap, and we can group them by the same items, generating one relation with the groupings. So in fact, there is no great difference between group and co-group, because Pig allows us to use group with multiple relations, or it allows us to use co-group with a single relation. But in general, the idea that it would be more readable to use co-group for multiple relations. So we then have aggregate operators, like you would know from SQL, such as take an average over the bag of values from the tuple, take the min, the max, the sum, the count, the size, or concat. So what's the difference between count and size? If you do a group by, there's no difference, because count will count how many things are in the bag, and size will count how many things are in the bag. The exact same thing. The only difference is that size we can also use as a function, as an operator on other types of elements. For example, we can get the length of a string using size, or we can get the length of a tuple using size. So size accepts also not just bags, but other things, and will give you the length of the tuple, the string, and so forth. So, but we can use both in the context of grouping, of aggregation, because both will give you the number of elements in the bag. Okay. So next we have joins, which are of course a key operation in relational databases and in data processing in general. So here we have one data set containing some products. We have another data set containing, let's say, prices related to that. So what we have here is a product, an hour, and let's say a customer ID. And here we have the price and we have the product. So what we'd like to do then is get maybe the price per hour, for example, but we want to join these two data sets. So what we can do is load our first data set, data 1, as follows. Then we can load data 2, as we see here. Sorry, this is not customer ID. This is the number of products that were bought at that point, or how many times Nescafe was bought between 8 and 9 in the morning. So this is the count of number of times bought. So in any case, what we want to do is the same. We want to join the two. So to do a join, we can just call join A by whatever the join key is in data 1, which would be the product, and B by name, which is the name of the product in the second relation. So we're going to join this column here with this column here to produce a joined relation. So what will we get as our output? We will get we have one row for Nescafe here and 2 rows here, so that would be 2 rows for Nescafe. We have nothing for Gillette here, so that's 0. And then El Mercurio, we have 1, so we should expect to have 3 rows in our relation here. So yeah, so this is a typical relational inner join. Okay. So join A by whatever the join key here is in B by whatever the join key is in B. And here's how the data will look, right? This is the part that comes from A, and this is the part that comes from B, or data 1 and data 2. So can we do other types of joins? So we saw essentially that the default is to do inner joins as it is in SQL, but we can also do self joins. We can do outer joins, and we can do Cartesian products as well if we want. So what is a self join? A self join is just joining a relation with itself. So to do that in Pig, we need to make a copy of the relation, and then we need to join with the copy. We can't directly join one relation with itself. We can't say A join A, for example. So we can't have join A by product, A by product. We can't do that here. Why is that? Because we have streaming relations. And essentially, once you've read the file, you can't read it again. Somehow Pig won't let you read it again to do the join. So you need to create a copy of A. So it would be join A by product, A copy by product if you wanted to do a self join. Outer joins, you can do left outer joins, right outer join, full outer join. So hopefully you remember what those are from SQL. From relational databases. And you can also do a Cartesian product, which will just combine all of the rows from A from all the rows of B. So if you had, I don't know, 300 rows in A and 500 rows in B, then you would have 15,000 rows in A cross B. So hopefully you remember with the left joins, right joins, full adder joins from SQL. Okay, so I'll assume so, but you can maybe refresh it as well you can let me know in the forum or whatever. So the full adder join being the union of the left and right adder join. Okay, so we can do various types of joins as you can do in relational databases. And there's a pretty intuitive syntax for that. So we can also mess with some underlying aspects of how the MapReduce job will run. So we can, for example, define a custom type of partitioning, which would be specifying a user-defined function, or we can use we can specify how many reducers we want to use to identify the amount of parallelism that we want for the reduction. So we can set, for example, that we want 5 reducers, which means that our output will be split over 5 different machines, or we could specify 1 if we think our output won't be that large and we would really want 1 file to be the output. Let's see if I can get the chat. Okay. No, sometimes my chat disappears behind some window. I don't know where it's gone. So let me see. Sorry. There. Okay. So in previous cases, full adder join would have printed Gillette Mach 3 and then empty spaces. Exactly. Yeah. Yeah. So in this case here, it would have created Gillette Mach. It would have been null. Oh, no, sorry. Gillette Mach 3. No, sorry. Null 500 to 8,250 Gillette Mach 3. So we would have kept a result for that. That would have been a right join because data 2 is on the right. So we'll keep the stuff on the right. And then if we don't have anything on the left, we fill it with nulls. So in this case, a right outer join would keep Gillette Mach 3. Yeah. Okay. Sorry, this is a completely different example. Anyways, almost the same one that we've seen. So yeah, what happens if we join 2 tables where we actually have the same name twice? Before this was called product and this is called name. So now I've changed it. So this is called product name and this was called product name here, product name. So we do a join, okay? And then that generates a relation X. So if we try then to somehow reference product name, we don't know if it comes from A or if it comes from B. Actually, in this particular example, it doesn't matter because the join is an equi-join, it's an equality. So it'll always be the same whether we use A or B, but still there's some ambiguity here. So this will actually return an error for us. So in the case where we have a relation that's joined and we've produced something, the same 2 columns with the same name, we need to disambiguate. And what we do is we will usually use the name of the original relation from which it comes, followed by 2 colons. So A colon product name. And this will work, right? So this will generate then the product name from A. So we can use this operator here to disambiguate from which column we're referring to in ambiguous cases. And if we try to refer to a column for when we have 2 columns with that name, it will throw an error and ask us to be more specific. So in this case, we return the product name from A, which would be this here. Okay. Another operator that we have is split. So if we use split, then we can create 2 relations. It's almost like the opposite of a union somehow. Or it could also be the same as applying 2 filters in sequence, right, over one table. So let's see an example. So we're going to use an UDF to remove the $ from the price and just return it as an integer. And then we can use split. So here we have a list of products. We have some prices. We can split then using this call here, okay, which I've not actually stored, but we can split numeric this entire relation here into one relation for cheap products and another relation for premium products based on the price. So if the price is less than 1,000, we'll put the row in here, and if it's greater than or equals 1,000, we'll put it here. So this can be, I'm not sure exactly how clever Pig is in its optimization, but this is potentially faster than having two filters in sequence, because we can read each tuple here once and assign each tuple to the corresponding output relation. So we can, split one relation into several different output relations with one read. It's possible that Pig is clever enough to optimize if you have a sequence of filters rather. I'm not sure, but in this case it would be certain to only do it in one pass. We can apply a ranking function if we want. So we can generate, for example, here we are removing the price, and we can rank then the products according to their price. So this would be calling rank numeric. And what this does is essentially it just adds the row ID. So probably it would make sense after we've ordered, for example, but we don't necessarily even have to order. In this case, we don't. So we just essentially add a row ID as a column to our table, which can be useful when processing data. If we want to, we can rank and order. We can order and rank at the same time. So we can call rank numeric by price ascending, customer descending. So we actually sort the table first according to these criteria, and then we add the row ID. In this case, if there is a tie, it will add the rank as being the same. So we'll have 3, 3, 3, and then 6, 7, 7, 9, and so forth. Okay. So this can be pretty useful when processing lots of data as well. So other operators, some of which we've seen in previous examples, we can filter tuples by an expression. We saw that earlier with price. We can return a certain number of tuples, so we can just apply a limit with some number to say take the first n tuples of the input relation. We can, if we wish, call a native jar in the middle of our script. So if there may be something that we've already coded in MapReduce and we just want to call it as part of our Pig script, we can do that. Order by, which we've actually seen. Sort tuples in examples. We can take samples of tuples if we want to reduce the output. Take a large input relation and take a sample of those as the output relation. We can apply union, which is to concatenate two relations. So there are some other operators that are more or less familiar from SQL, for example, and some of which we've seen from the examples previously. So any questions? Okay. So I've spoken before about nulls, how we can have incomplete information. So here we have an example of incomplete information where the third value here is missing and the first value here is missing. So if we dump our table, we can load it in and dump it out again, and we'll see that we're still missing the data, right? So we can have nulls. It's not necessary to have complete rows. So what happens with nulls? What's the kind of semantics? How are they treated? So they behave as if they were nulls in SQL. So we have example of two data sets here where we have a nulls here and we have nulls here. And if we load these data and we try to apply a join, any guesses on how many tuples we're going to return? If we apply a join now where we're joining A on product name, which is the first column here, and B on product name, which is the second column here. So the first question would be, will this tuple here with a null join with anything here? Will it join with everything? Will it join with just the null here? Will it join with nothing? Okay, so in SQL, it would be the same as what happens in SQL. And what happens in SQL is that nulls are not equal to anything. Nulls are not equal to other nulls. They don't coincide. They don't match. So essentially, it would be, if we apply a join in this way, it would be as if we had filtered all the rows that have nulls in the join keys. Okay, So what this means is essentially all we get back is the join on element curia, which doesn't involve nulls. So this null here doesn't join with anything. Sorry, this null here doesn't join with anything, and this null here doesn't join with anything, and nulls don't join with nulls, so they don't join. The only thing is the complete join that we have here. Okay. Of course, if 500 here were null, then this would still be a join where this would be null because the null is not in the join key. It's just some value that is carried along. So it's the same as in SQL. Let me see how we're doing for time. Yeah, okay. So any questions or doubts? Okay. So last thing, second last thing would be how do I run my pig script? What's the process like for how do I develop or run pig scripts? So there's essentially the whole idea is you have some pig commands, and those pig commands will be translated to MapReduce in Hadoop. So it's an interface or scripting language for MapReduce. That's the first thing to make clear. It's not a different framework. It's not like there's a whole pig distributed file system and all of that that's different. No, it's all just a scripting language that sits on top of MapReduce. So the pig framework will take your script and translate the commands into MapReduce jobs. So there are three ways to execute pig. One way is to execute commands interactively, which is a great way for developing, but you should do it probably only for small files. So take a small file for testing first, and you can enter a grunt command line, and you can just enter your commands line by line. It's always a good idea to just make sure you copy the commands you're using as you go into a text file. So in case your script goes wrong or grunt falls over the command line, you still have a record of what you were doing up to that point. So in any case, yeah, you just continue line by line, defining your commands. And then when you're done, you can store, you can dump, and so forth. So you'll see this in the lab. This is a great way to develop your script over a very small sample of a file, for example. And then later you can just take your script and change this input to the full size of the file. So we'll see this in the lab. The other way is to store your script. So this would be maybe after you've developed your script over a small file, you can store all of the commands, just change the input to give it to the full file. And then you can run your script with just calling pig and the name of the script that you've created. Okay. The third way would be embedded. So you could conceivably, as I mentioned before, you can call MapReduce, like Java MapReduce jars from pig, but in the other direction as well. From Java, you can also call pig, which is not a typical way at all to execute pig, but you could conceivably call pig from Java code, for example. But the most typical way would be these two here: grunt for kind of developing line by line your process and testing it and previewing the output, and then a script for just running the final thing over a large file. This would not be typical, but it's possible to do. So that's the overall view of the pig scripting language. There's more information in the docs, and it's something as well that you'll play with in the lab. So to mention that there is another alternative which is quite popularly used as well, which is Apache Hive. It has this very same idea that why not use a language like SQL rather than something like Java to implement the MapReduce jobs. So this is an example of a job written in Hive. So we see it's a little bit more similar to SQL, but it has certain elements that are different. For example, here we're doing a word count and we're splitting words and so forth. And there's some new calls like lateral view. So this is quite popularly used as well, but I actually quite like for me, pig is more intuitive because of this line by line way you can process your relations. There is one thing also that's nice about pig is that it evaluates relations lazily. So actually, when you're calling these commands here, it's kind of important to mention that it's not going to immediately launch a job on Hadoop until you call something that expects an output, for example, store or dump. When you call that, then you need to produce some results, and then it goes back and checks all of the chain of commands that lead to, for example, this relation needing to be computed. So in that moment, it will actually launch some MapReduce job for you. So it's a lazy evaluation. So, you might be processing lots of data here and you call load and it does nothing, right? So you might be surprised, right? That's because it has done nothing. It just remembers the command. And then when you go to store or read or to output something, it will execute all of the commands, the chains of commands that are necessary to produce that relation and that output. So sorry, in any case, I quite like this line by line paradigm versus trying to create a kind of a query like this. It's more similar to SQL, but I think Pig is more intuitive, but both are very commonly used in practice. I'm not going to speak about both because they're very similar concepts. And I think you could easily, once you know about Pig, you could easily pick up Hive if you need to use Hive in another setting. Again, in Hive, it compiles these sorts of tasks or queries into MapReduce jobs in Hadoop. So Pig is a bit more procedural, like you have the sort of line by line transformation of relations, while Hive is a bit more declarative in that you can specify kind of more complex queries that will be translated. I'm not sure which you prefer, but in general, I think Pig is more intuitive and easier to work with. So one thing to mention in general is that, why teach or talk about Hadoop and Java if you have these high level scripting languages that are a lot easier to code for and so on. In general, in the projects I've seen, that in most groups who decide to work with Hadoop, they generally tend to work with Pig, almost all, or they select Spark or something else. So why talk about Hadoop in Java? Essentially, it's the sort of production way in which things would be implemented. So if you have a process, what I would say in general, this is a very general rule of thumb, but if you're working in a company and you have this regular batch processing that you need to do, for example, you're working with IMDb and they want to, very regularly compute some large statistics over which are the best movies every week or something like that. You define some process for that or some analysis. If you're kind of regularly running something that needs to be done efficiently at large scale, then Java allows you to really optimize a lot of details of what you're doing. There is a cost associated with Pig because there's an automatic translation that might not always be as good as optimizing the resulting MapReduce jobs as an experienced programmer. So in general, Pig is good if, for non-experts who are not good with Java, but also for, maybe once-off tasks that you're only going to run once. So in that case, it can be quite, if you find Pig more intuitive to work with, you can code in Pig and run your script, and it doesn't really matter if instead of 6 hours, it takes 8 hours, right? You don't really mind maybe too much. So it has the benefit is kind of easier to develop MapReduce jobs, but it can come at a cost based on perhaps not being as optimized as or optimizable as something you code in Java. Okay, so with that, I'll stop talking. Any questions or doubts or thoughts? Yep.
Me preguntaba cómo es que uno toma la decisión, por ejemplo, en qué momento uno dice, ya, una base de datos relacional ya no me sirve, tengo que ocupar algo no SQL. Me imagino que no es fácil la respuesta.
No SQL. Okay. So that would be. Yeah, no SQL we'll talk about a little bit later. So I wouldn't answer that right now, but we'll get to that in the second part. But it's mainly an issue of scale and the types of queries you're running. If you're running very simple queries at very large scale, no SQL is the option. But in terms of Hadoop, like when to use Hadoop and when to use a relational database, yep. So in that case, it's essentially, you could do it by experience. You could just try in your relational database and you might find that something is taking way too long, like several hours, or you might find that it's just taking up too much time, like too much processing in your relational database. You don't want your relational database to be occupied for several hours to compute this query. In that sort of case, it can be a good idea to move to Hadoop. If you don't want to go through that experience of trying a query that's not going to work, in general, you can try to think about the way in which it will be processed, the query. So how the join will be done and how many random accesses it will create on disk. A general rule of thumb is that most databases are not really designed for doing joins on relations with, hundreds of millions of rows, for example. Like, unless you select something first, you say, okay, I want all the data for this employee, that works well in a relational database. But if your task is more like across all the employees, I want to join with the table for products that they've sold, and I want to sum the values of all those products. And if those tables that you want to join on contain, tens of millions or hundreds of millions of rows, you're probably going to have problems with a standard relational database, just due to the way that it generally assumes that your query is going to be about a specific employee, a specific product, and so forth. And it will try to give you a real-time response, right? It tries to be very fast at answering these sorts of queries. It's not really designed for these more batch processing type tasks. So, I mean, the simple question is, do it in a relational database until it no longer works. In which case, maybe then you need to start using Hadoop or something. But Hadoop is also quite reliable in the sense that, for these sorts of queries that we've seen and the sort of analysis you've seen in lab 3, it will work and it will run as long as the cluster is working fine. But it's reliable. It's kind of slow and reliable, right? So you'll have your answer in 20, 30 minutes once the thing starts processing, or in several hours. It's sort of, you're just sorting lots of data, which is a very reliable process. Whereas in relational databases, they're complex systems and they have a lot of things going on with respect to the management of transactions and so forth. So there's a lot more overhead in a relational database. The other thing as well is that relational databases can't really leverage the power of multiple machines very easily. So the sort of simpler form of processing that Hadoop uses, which is just sorting data to do joins and aggregations, can be distributed more easily over multiple machines, and it's somehow reliable by its simplicity. So when to use a relational database, you can try it in the relational database. If it doesn't work, try it in Hadoop, and maybe eventually you'll get an idea that of what sorts of queries relational databases can or cannot do.
Y un sistema, por ejemplo, que ya esté funcionando, que sea transaccional, tener una copia de los datos para hacer como big data sobre eso, ¿es una buena idea?
Yeah, I think in general the limiting factor in terms of like where does it break down? It breaks down because of what we spoke about in the first class, that the relational database might end up deciding to do lots of random accesses based on index nested loop joins. Like, take a tuple from this table and look it up in the other table. Take the next tuple and look it up. And if that turns into random accesses on the disk, then every random access takes 100 milliseconds and you're kind of in trouble. Now, there are other ways where there are sort merge joins where the relational database could say, actually, it's better to sort these two tables and just join them using a merge sort, which is exactly what Hadoop is doing. But it would be, I would say, quite rare that it would opt for that, and it's not optimized for that. There's no really very concrete difference. Of course, in a relational database, you could implement all of the stuff of Hadoop underneath, right? And that's your relational database. But typically speaking, in practice, your limit is going to be that your relational database is going to generate a lot of random disk accesses, and they are going to be slow. So copying your relational database and putting it on another machine and running your analysis there, my point would be it could work up to a certain point. But you will reach a certain point where it's just not feasible to run on the relational database, even if it has sort of the same sorts of joins underneath as MapReduce is using, which would be sort merge joins as opposed to hash joins or index nested loop joins. If it uses the right type of join, you're still limited because it will probably be only running on one machine. Like Postgres, for example, MariaDB, MySQL, you're going to be limited in that you're only going to be using one machine. So then at that point, what you really need to do is to do these sorts of joins on multiple machines. And that's what Hadoop is doing for you. But if it's working in your relational database, continue using your relational database. I would say in general that this sort of processing or big data in general refers to the idea that there's nothing else. It's sort of like you can't use conventional technology. So you're not really, if it works in a relational database, I would say by definition, you're not working in big data. You know what I mean? I would always use that as a good rule of thumb that if it's working okay in Postgres, you don't have big data. That would be a fair definition. Yep. So kind of a long answer. It's a complex question, but hopefully I got across some of the ideas. And it's a very important question as well. So, any other questions or doubts? Does Pig look nicer than Hadoop? I guess you'll have to see the lab first. You'll have to get hands-on with Pig. Yeah, so in the lab on Wednesday, we'll look at Pig. So I think in general, hopefully the previous lab with Hadoop is going okay. I know it's a bit longer, maybe more complicated than what we've seen, but it's a very important lab as well. So, but if you have any doubts or questions, you can ask in the forum or let us know. Hopefully the cluster is working a bit better. So now you see the instructions in the forum and how to view the queue of jobs and so forth. So that way you can sort of debug what's happening or figure out why your task is just waiting endlessly for something to happen. You can also kill jobs if you want, but do be careful. Try not to kill jobs that are actually doing something. You only kill them if it seems they're really stalled. Questions, comments? Okay, if not, so see you on Wednesday in the lab. So we'll play with Pig. So see you. Sorry. I see questions in the chat now. Is it possible to tell it to run something before, something like a run command? You can run a script from Pig. So you could have a Pig script called from within the Pig terminal if you wanted to run some pre-existing process before, or you could even run a MapReduce jar. So you have a run command both for Pig scripts and for existing Pig scripts and for existing MapReduce jars if you need to. So what dump does, as you saw in the examples, is it just prints to the screen the full relation. You definitely do not want to do that if you're working with a lot of data, but if you're working with an example, it can be nice to just see in the screen a sample of the data, what the output data will look like. So dump will execute anything that sort of outputs or externalizes or requests it asks what data are in this relation. In that moment, Pig will execute everything that's needed to generate that relation for you. So if it can get away without executing something, it will do that for as long as possible. And only when necessary, it will execute the commands necessary to compute a relation. So dump is one of those and store is another example. So why does it do that? Because sometimes it can combine multiple commands into one part. You might have 3 commands in Pig that correspond to one map. So if it were to try to execute everything line by line, it might end up doing 3 maps in sequence, 3 MapReduce jobs when it could just do 1 map combining everything. So yeah, it evaluates just as necessary, lazy evaluation. Sorry, I couldn't see the chat at the time. Sometimes the chat window just disappears. I'm not sure how to recover it. Okay, so see you on Wednesday. Bye-bye.
Chao, profe.
Ciao.
Chao.